Okay, good morning.
Good morning.
Today we're going to talk about chapter 9. It's about natural coordinates and numerical integration. Okay? And as you can see from the previous lectures, in finite element we need to integrate to obtain the element stiffness matrix. Okay? That is because we are dealing with a continuum body, and every part of the body will contribute to the energy of the system. So you need to add them together. Add them things together means simply integration. Okay? In calculus course, we learn how to perform integration. We usually do a lot of exercise and try to get it. And the unfortunate fact about integration is that you're not guaranteed to obtain a closed form solution in general. For differentiation, if you can write the expression, you can always obtain a closed form expression for differentiation, but not the other way. Okay? Integration is not guaranteed. Actually, for a lot of cases, it's impossible to find a closed form integration expression. Okay? But there are ways to get around that. What we can do is to integrate things numerically. It turns out, as long as you can write the integrand, you can always do a numerical integration. So that's what we are going to focus today. Okay? All right, first let's start with 1D. 1D integration and change of variables. It is desirable to integrate using the local natural coordinate system, because when we use the natural coordinate system, the boundary for integration is always from -1 to 1. So that can standardize the numerical integration procedure, which is a very important thing to do. Okay? But let me first remind you of the change of variables formula in calculus. If, say, we are going to integrate a function f of x from a to b, okay? We desire to change the variable x to another variable. So let's say we can express x as a function of another variable. Let's call that theta. Okay? And then what we will do is we'll substitute x as a function of theta in that expression, but we need to do something else accordingly. We need to do, in addition to substituting this in here, we also need to make sure the integrands, the limit for integration are changed accordingly, and also these dx also need to be changed accordingly. And these changes to theta 1 and theta 2. Now f is a function of theta. So this is a composite functional relationship here. At the end, you can view f as a function of theta now. Right? And then here dx, we need to express as dx and then d theta and then d theta again. And this is very important. So don't forget this thing. This is called actually the Jacobian. Okay? Where a is equal to x of theta 1. B is equal to x of theta 2. So that means when the new variable is at theta 1 and the x is at that limit in the original lower limit, when theta is at x2, x is at the original upper limit. So this is the corresponding positions of the integration. Okay? I believe you've learned that in the calculus course. Okay, now let's look at the element stiffness matrix from chapter 6. We derived the element stiffness matrix. So we are still using this 1D example. Okay, this is I and then J here. This is the element. And the formula is this: A, E, and then integrate from 0 to LE. And this is the B matrix, transpose. And then B, and then dx. Of course, when we write it this way, we are using the global coordinates, right? So this is in global coordinates. Now, we desire these to be written in, to be integrated in the natural, local natural coordinate system. So A, E, these are constant. Let's just write that. When x expressed as a function of the local coordinate system, theta, its limit goes from -1 to 1. So this becomes -1 to 1. And B, now you need to view it as a function of theta. Here, you will view it as a function of x. But at this point, you view it as a function of theta. Okay? Then, this dx here, don't forget the Jacobian here. That's the dx, d theta, and then d theta. D theta. All right. Previously, we have derived the relationship between the shape functions and the global x, and also the shape functions with the local natural coordinate theta. We've derived that. Let me remind you of the relationship here. In global, this n shape function is equal to I think it's xj minus xi, xj minus xi. So this is the first one. And then we have xi minus x, and xj minus xi. Let me see if that's the case. I think there is a negative sign in front. Or x minus x. X minus x I. Okay. This is in the global coordinate system. In the local coordinate system, it is natural or local, and is equal to find that out. 1 minus theta half oh, the second one is +1. Thank you. Yeah, it's something like that. Okay? So this is in the global coordinate system, this is in the natural coordinate system. Alright. So once B is simply a derivative. B by definition is d dx n, okay, with respect to x. And it turns out the B is a constant. So if it's a constant, it doesn't matter whether you viewed it as a function of x or a function of theta, it remains the same. So this is simple, it's actually a constant. Now, what about dx d theta? In 1D case, we have a formula which says x is equal to x middle point plus half the length times theta. That's the formula. However, for more complicated case like the 2D case, a simple formula like that will be the formula is not as that simple. What we do is we can use the same shape function which interpolate the displacement between the nodal values and the middle values, and we use the same function to interpolate the x coordinate, okay, between the nodal value and the middle value. So here we propose to use the shape function to interpolate x. It means x, we're going to use n1, ni, which is the left node shape function, and times xi plus nj xj. Okay, now you can see here, ni is viewed as a function of theta. nj is also a function of theta. These functional values, these nodal values xi and xj, they are not they are parameters. Okay. Once the node position is given, as far as integration is concerned, they are constant. So what is changed is the natural coordinate from the left end up to the right end. So this, you can view it as a function of theta. So x is now a function of theta. And we know that it will work because when theta is at the left end at node I, ni is 1. That's the property of the shape function. So this is equal to 1, and nj is 0. Therefore, at the left node, when theta is -1, you recover xi, which is what it should be on the left node. The nodal coordinate, the global coordinate should be xi, right? On the right node, this shape function is 1. This shape function is 0. So x recovers xj as it should be. In between, because this is a linear function and another linear function, all linear functions, a bunch of them add them together is still a linear function. So you know it is guaranteed that from the left end to the right end is changing linearly, and the two end positions are correct. So these must be correct. Okay? So this is a very useful formula. And if you look at this and compare that with the displacement interpolation function, which is u is equal to n I ui plus nj uj, you can see it's the same kind of formula. Okay, this is an interpolation from the nodal displacement to a generic displacement. This is the interpolation of the nodal position to a generic point position. We are using the same function. And because of that, actually, the element that we are going to develop is called isoparametric. Okay? And you may see in the literature this name, isoparametric. It means you use the same shape function to interpolate displacement field and the coordinate. Okay. All right, once we have, this gives us the relationship between theta and x. Once we have that, of course, now we can calculate that derivative, right? We need a dx d theta. All right, so dx d theta is equal to, now we can substitute this expression in, and I is a function of theta, but xi is not. So it's d ni theta d theta, and then xi plus d nj theta d theta xj. And I is this one, d theta is equal to negative of xi. Here, d and j, d theta, this one is plus half xj. Okay? We also know that this is equal to half xj minus xi. But xj minus xi is exactly the length of the element, so it's half Le half. Alright, so now we have this one. Okay? And this is constant. And we obtain that. So we can plug that in. The integration is always from -1 to 1, so it's very easy to do. At the end, let's just do that. So KE is equal to AE -1 to 1. Let's write down this B expression. B is the derivative with respect of n with respect to x. When you plug in here, the first one is -1 Le. The second element is this with respect to x, which is 1 over Le. So this is transpose. Okay, this is the B transpose. And B here -1 Le, 1 over Le. So instead of writing it transpose, I already write it as a row vector, so it's been transposed like that. Initially, it should be a column vector. And then times this dx d theta, which is half Le here, and then d theta. Okay, this is the formula for the element stiffness matrix integrated in the natural coordinate system. Okay? And of course, this is a very simple integration to do, because the integrand is a matrix which is 2 by 2, but every element is a constant. Okay? At the end, KE, we can write everything out is equal to AE. This is 2 by 2. And the first, let's look at the first element, is this times that. So it's 1 over LE squared, and then times this, and half. So is 1 over 2 LE. And that's a constant, we can take that out. So at the end, the integration is 1 d that, which means it's theta, okay? And the limit is from -1 to 1, so it's just 2. At the end is actually 2 times 1 over 2L is 1 over L, or 1 over LE. This is the first element. And the second element is this times that, which is negative. And this one, 1 over LE, 1 over LE. Okay? All right, simple enough. We can also write it as AE, LE, 1, -1, -1, 1. We have come across this expression multiple times before. So the important thing here is to show how to express the integration of the element stiffness matrix from global coordinate to the local natural coordinate system. Don't forget this Jacobian here. So this is the important thing. The limits are changed correspondingly. Okay? All right, this is a very simple example, 1D, and the integrand is actually constant, so it's not much to worry about, and it's very easy to do. Now, when it is 2D, and when it is also higher order element, you may not have such simple things. First, the integrand may be a real function of x or theta. It could be linear, quadratic, and cubic, depending on the order of element that you want to use. And it is also 2 by 2. In 3D case, is 3 by 3. Then what do you do? Well, when the integrand is a more complicated function, we really need to derive more accurate and real numerical integration formula. Okay, that's what the next section is about. It's called the Gauss-Legendre integration. And for short, we just call it Gauss integration a lot of times, okay? Let's review the concept of integration. Let's say we have a function of x that goes from A to B like that. What do you mean by integrating the function f of x from A to B with respect to x? Graphically, what does it represent?
Area under the curve.
The area underneath the curve, exactly. So, okay, so it's the area underneath this curve. Well, if you have a simple functional form, then you can do it, you can integrate that actually in closed form, okay? And you can get it. Now, if the integrand is more complicated, sometimes it's just impossible to integrate that. However, conceptually, we can always say that, well, if I want to calculate the area, I can, to a very crude estimation, I can just pick maybe this point or that point or maybe the middle point as the height. If I pick the middle point, this is the height times this base, I have a pretty good idea how much the area is, right? If I pick the middle point here, and then times the base, effectively what I'm doing is I represent the area by a rectangle like this, right? And so the formula becomes f and x middle point times the base. The base, I will call it h, okay? H is b minus a. That will give me a rough idea how much the area is. Most people will do that, right, if you have a real problem like that. Now you can see, if you do that sometimes, here I underestimate area by that much. Here, I actually underestimate the area by this much. Okay, if I desire to improve the accuracy, I can add more points. Maybe I can make 1 point here, 1 point here, and measure the length. Now the length is here. This length is here. So maybe from here to there, I can do okay. If I do that, well, let me be systematic. This time, I have 3 points. The first area I will do is to pick this height and times this area. Okay, it will give me that. And as you can see, this is underestimated. The second, I will take this height times this length. I get this area, and then I take this height and times that, I get this, and I take this height and times that. So I get these 4 areas together. The basic idea is still pick some points within this interval and calculate the height, which is this. The function value of that is the height. And times some kind of weight. Okay? And then I'm going to add them together, right? So numerical integration actually conceptually is very, very simple. You just evaluate the integrand function at certain point and times an appropriate weight, and then you keep doing that at a bunch of locations and then add them together. If you do it, if the weight is selected correctly and this is also selected appropriately, at the end you should have a pretty good idea. You should have a number that is very close to the area that you want to estimate. Okay, so that is numerical integration. Therefore, let me write it here. Numerical integration means perform a summation with the expression that x is evaluated at certain point times the corresponding weight. Now the summation is from 1 up to number of integration, 1 to n. Okay, so that is the numerical integration form in principle. In fact, all the numerical integration formula can be expressed by this way. It doesn't matter whether it's the Mittal formula, the trapezoidal formula, the Simpson's formula, the more elaborate Newton-Curtis formula, and the Gaussian formula that we're going to talk about here. Okay, so this is a generic form for all numerical integration. Okay. Oh, pen is here. Well, it turns out many numerical integration forms, they utilize evenly spaced points. Okay, just like here, you just divide it. This you divide it into 4. You have 3 internal points and 2 end points. And then you can keep dividing that. But they are all evenly spaced. The trapezoidal formula, Simpson's formula, and all Newton-Curtis formula are evenly based. And Gauss and the Zander, they came up with a clever plan. They argue that evenly based numerical integration is not the most efficient. Depending on the shape of the function, if you cleverly select some points which are not evenly spaced, you may get a higher order integration, integration of high order accuracy. Okay, so that's the basic idea. So I will write it here: evenly spaced, like those trapezoidal, Simpson, and also Newton, Cotes formulas. They are all evenly spaced. Now the uneven space. Oh, this is unevenly spaced. Is the Gauss Zehnder formula. Okay, how to derive that is actually very simple. Once you understand the idea of a numerical integration, you understand what Gauss-Zehnder tried to do, then you can derive the formula. Okay, let's say so now x, which is the evaluation point, and weight function wi, both are variables now. So the idea is to solve for those so that the integration will be exact to the highest possible order. Let's talk about a two-point Gauss integration. Okay, so now we will have the variables or the unknowns will be the two positions, x1 and x2. And then the weight, w1 and w2. Well, because we try to express everything in terms of natural coordinates. So let's start with the natural coordinate. Everything is now in the natural coordinate. So I will write the position as theta I instead of xi, okay? So it's theta I and then wi. So the formula will be this. Function of theta integrate from -1 to 1 d theta 2 point. That means f at theta 1 times weight w1 plus f at theta 2 times weight w2. Okay, so that's the formula. What we desire is that these formulas should be accurate to first a constant function and linear function. Because we have 4 variables, we can go up higher. Quadratic function and even cubic function. So that's possible because there are 4 types of formulas, right? 4 types of functions. So I have 4 conditions. I have 4 unknowns. So I can possibly satisfy that. Let's see if that is true. So when f is equal to 1, we require the formula to be accurate. And we know that integration of this 1 with respect to theta from -1 to 1, the left-hand side is equal to 2, okay? And that's equal to, the right-hand side will be, this is 1, right? 1 times W1. This is 1 times W2. So this is equal to the right-hand side. Okay, this gives me one equation. Next, I will let f equal to x, which is a linear function. And I put in here, oh, not x, theta, because I'm using natural coordinate. So this is theta. Integration of theta is very easy. It's half theta square, right? Half theta square, and then you put the limit 1 and then minus limit at -1 is also equal to 1, I think. Check. Oh no, half theta square. So it's symmetric. On the left side is equal to the right side is equal to 0. Left hand side is equal to 0. The right hand side is what? This is equal to theta, and theta 1 at that location is equal to theta 1, W1, plus theta 2, W2. That's the right hand side. Okay? All right. Let me now let f equals to theta square. Theta square, the integration is 1/3 theta cube. 1/3 theta cube, put in the two limit 1 and -1. The left hand side is equal to actually 2/3. The right hand side is the integrand, which is theta square. First is at position theta 1, so times weight 1, plus theta 2 square, weight 2. Right? Alright. Now let's see. And that will be it. I cannot hope. Oh, I only have 3 equations, so I can go up higher. Okay. So now I can also let f equals to theta cube. And the left hand side, this is an odd function. When you integrate the odd function with, even with symmetric integrals, okay, from that side and the right side is equal to 0. So that's again 0. And the right hand side becomes first one theta 1 cube and times weight 1 plus theta 2 cube and W2. Alright, let me box this. This is a total of 4 equations. How many unknowns? W1, W2, theta 1, theta 2, 4 unknowns, solvable. However, this is not linear, a system of linear equations. You see, you have these higher order terms, so you may need some special trick to solve it. Well, first we will observe that there's this one and that one. So we can write these equations, they are both equal to 0. So these are homogeneous. We view the variables is W1 and W2. So if we do that, we write it in this form, okay? W1, W2, this W1, W2 in matrix form. So equation, we call it 1, 2, 3, 4. 1, 2, and 4 together. I can write it as in the matrix form. Theta 1, theta 2. Here, theta 1 cube, theta 2 cube. And then times W1 and then W2 equals 0. And how to solve that equation? It's linear in the weight, but nonlinear in the coefficient matrix. For these, obviously W1 equals 0, W2 equals 0 is a solution. But that's trivial, it's useless for us. We want non-trivial solution. In order to have non-trivial solution, remember what kind of condition do we need? For this to have non-zero solution, we need the coefficient matrix to be the determinant of it to be 0. Or the coefficient matrix must be singular, otherwise it will be just trivial solution. Therefore, for non-trivial solution, we need this equals 0. Okay? From that, we derive that will be either theta 1 is 0 or theta 2 is 0 or theta 2 is equal to plus minus theta 1. Because obviously when theta 1 is 0, this column is 0, the whole thing is 0. When this is 0, the whole thing is 0. Or when you satisfy that, that's also 0. This is this is not useful for us. And this one, we want theta 1 and theta 2 to be different point. So we only select the we will select theta 1 equals negative theta 2. Okay? Into when theta 1 is equal to negative theta 2, in the 2, we find that W1 should be equal to W2. Okay? When W1 is equal to W2, it means, and then into 1, it means W1 must equal to W2 is equal to 1 from this condition. And then finally put into equation 3. Put in here. Turns out theta 1 must be equal to 1 over square root 3. Theta 2 is equal to negative 1 over square root 3. Okay. This is the Gaussian integration. So it tells us that when you try to integrate something using 2 points, the most efficient way, as far as the best accuracy with polynomial is concerned, these are the polynomials, right? If you select a point at positive 1 over root 3, another symmetric point at negative 1 over root 3, and the two-weight function is 1, the integration will be accurate for linear function, for constant, definitely, for linear function, for quadratic function, and also for cubic function. So now only using 2 points, you can accurately integrate a cubic function, which is up to a cubic function, which is very nice, okay? Okay, let's see whether that really works. We can then use some example to verify it. Example. Okay, let's say we have a function f of theta that is equal to 100 plus 50 theta linear and then 75 theta squared. So this is a function, a quadratic function. Okay? Then we want to integrate it from negative 1 to 1 f of theta. This one is very easy to integrate. Closed form. So here, let me write it as closed form. The first one is 100 Chater. The second one is half 50 Chater square. The third one is 75 1/3 Chater cube, like that. When you integrate that in closed form, then you put in -1 and 1, or -1 to +1 there. At the end, you give the value of 250. So 250 is the exact solution, okay? All right. Let's use one-point integration, the midpoint. Okay? Of course, when you use 1 point, the most sensible thing to do is select the middle point. F will be evaluated at the midpoint. It will times the interval, which is 2. The midpoint is 0. Midpoint between -1 and 1 is 0. Okay, so we put 0 here. So it's 100 plus 50 times 0 plus 75 times 0 squared, then times 2. At the end, this gives us 200. And of course, this is different from that, so it's only an approximate solution. Okay, it's about 25% error. Now, if we use the trapezoidal formula, which is a 2-point formula, so it's -1 to 1, F Chater D Chater. Yeah, here I should write D Chater. Sorry for that. And this is equal to, the trapezoidal formula says pick the left point and the right point. So it's F at -1 and plus F at +1 and times the formula is this. If you have a trapezoid, you take the base and the top, add it together and divide it by 2 and times the height. So this is divided by 2 times the height. The height is the interval, which is h. Okay, that's the trapezoidal formula. H is actually the 2. So put this in, very easy to calculate. At the end, you get a number of 350. So this formula actually overestimate the original integration. Now let's use the Gaussian point. Gaussian 2-point formula. Okay, -1 to 1, F Chater D Chater. Let's see what the formula says. The first function evaluate at this point 1/√3. So it's 100 plus 50 at 1/√3. Okay, plus 75 and then 1/√3 square. This whole thing times the first weight, which is W, times 1. Then plus the function evaluated at the second point, which is θ2, plus 100 plus 50 -1/√3 plus 75 -1/√3 and then square and then times 1. Okay, use your calculator, or you can even calculate that, evaluate that by hand. Turn out to be exactly 250. Okay. 250 compared to that. So as promised, if the integral is quadratic, it will be accurate. You add a cubic term and do it again, any cubic term, it will also be accurate. Okay? So this is a very good way to integrate it numerically. When you add a fourth order term, you will find that the closed form solution will be different from the numerical solution, but it's still pretty good, depending on, of course, the functional form. Another example, but remember that the Gaussian integration is derived in terms of, in view of using polynomial function. If it's not a polynomial function, it will not be accurate. It will be only an approximate solution, okay? So it only guarantees that if the function can be expressed in a polynomial form, it will be accurate up to the third order. That's what Gaussian integration promises, okay? Now, let's look at another example. If we want to integrate cosine theta from -1 to 1, this time cosine theta, when you express it in terms of Taylor series, it will be, you can express that as a polynomial function, but it's up to infinite terms, okay? Of course, the integration of this is sine theta, so you put 1 from -1 to 1 there. At the end, this is equal to 1.682942. Okay? Now use 2-point Gaussian integration. And again, we will first evaluate it at 1/√3 times the weight 1 plus cosine -1/√3 evaluate times weight 1. And use your calculator. This is equal to that, so it's twice that. At the end, it's equal to 1.675823. Okay, now you compare this number with this number. They are different. Even though it's a very simple function like cosine theta, the Gaussian integration will not give you accurate result in general, okay? But still, the accuracy is pretty good. It's on the third digit, which means is about 1%. It's actually, we think, less than 1% difference. So, which is pretty good, okay? All right, you can apply the same procedure to derive the Gaussian integration. Now you know how to do it. Up to any order of polynomial you like. Of course, if you want to derive a 10-point Gaussian integration, it will be very, very messy to solve the equations, okay? And in fact, if you use Gaussian point, there's rarely any need to go up to 10 points. 2 points is very good. It's all you can use in a lot of applications. Occasionally, you may consider using a 3-point Gaussian integration. A more efficient, a more effective way to do the integration maybe if you have a long interval, okay, you chop into smaller ones, maybe chop into 10 elements. Within each element, just use 2-point Gaussian integration. That would be very good, okay? Instead of using a long interval, the whole domain and use 10 Gaussian point integration, which is not the best approach. Okay. Chop into small elements, and each element using 2 or 3 Gaussian point integration. However, I would like to let you know that there are higher order Gauss integrations. Okay, let me write it here. Number of integration and position and the weight. If you use 1 point, it actually coincides with the midpoint formula. The position should be 0. The weight is 2. Okay? If you use 2 points, that's what we just derived. It is plus or minus 0.577350. You can, and the text list up to about 12 digits. Okay, I just write 6 digits here, and the weight is 1. This is the first 6 digits of 1 over root 3. Okay, if you use 3-point integration, is plus minus 0.774596, and then some more digits. And the weight function is 0.555555. And then one more point, which is 0. And the weight is 0.888888. Okay? So you have 3 points. One is at the middle, the other is symmetric. One on the left side, one on the right side here. And this is the corresponding weight. Okay, now we are armed with the new knowledge of numerical integration. We can look at the previous formulas and we do this KE, okay, which is B transpose, and then B from -1 to 1, dx, d theta, and then t theta. It turns out, because this is -1 over LE, this is 1 over LE, -1 over LE, 1 over LE, this is from -1 to 1. Here we have LE, and then d theta. Okay. Now we take this thing in a new way. Previously we have the same expression. We integrate it in closed form, sort of in closed form. Of course, constant is very easy. It becomes just theta itself, and we put a limit. But this time we take it from a different view. We're not going to integrate in closed form. We just use the Gaussian point. But because this is constant, you can use 1 point, 2 point, 3 point, doesn't matter. So use 1 point will be the simplest. Okay, this time. So let's now take a numerical integration point of view and rewrite the formula. Let me first rearrange things a little bit, take all the constant out. Now we have an LE outside, and this is -1 and 1, and this becomes 1, -1, -1, and then 1. Oh, there's I think a factor of 2 here. This is d theta, so there's 2 here. Okay? Now this time, instead of, even though it's so easy to integrate in closed form, I'm not going to do it closed form. I'm just going to do it numerically. So now I use numerical